honor of hosting this CACOR Live event. Nowadays, the increase of carbon dioxide concentration in the atmosphere is mainly discussed in relation to radiative forcing and the consequent global warming. However, CO2 is a chemically active molecule that plays a vital role in Earth's ecosphere. CO2 affects the acidity of seawater and has multiple effects on marine organisms. It is also a fundamental component of the photosynthesis and respiration reactions. There is evidence that higher CO2 concentrations can make the photosynthetic reaction faster in some plants, but also negatively affect the respiration reaction in aerobic life forms. The effects of this chemical and biochemical perturbation on the biosphere and human health may be more important than generally highlighted in the current discussion. These considerations stress the importance of rapidly reducing CO2 emissions and, whenever possible, removing the excess from the atmosphere. They also show that geoengineering techniques based on solar radiation management alone cannot be sufficient to control the disruption caused by human CO2 emissions. Our speaker, Ugo Bardi, is a polymath who has interests that go from ancient history to the future of humankind. After a career as lecturer in the School of Chemical Sciences at the University of Florence, he is now active as a member of the Club of Rome and the World Academy of Arts and Sciences. He is the author of several nonfiction and fiction books that deal with the future and what it has in store for humankind. The most recent one, in English, is Extermination, with the title being self-explanatory. Ugo, you now have the floor.
Thank you very much, Claude.
So let me show you a few things on the whiteboard here, and I'd like to tell you some details on how this molecule, carbon dioxide, interacts with the whole biosphere, or better said, ecosphere, which includes the inorganic part of the area surrounding the Earth, volume more exactly. So you know that Earth is a big ball of rock surrounded by a thin layer of things, the biosphere and the atmosphere. Now, of course, the biosphere interacts with the atmosphere with breath. We will not survive without an atmosphere. And the atmosphere composition is everything. So you know, you have studied it at school, that atmosphere is mainly composed of nitrogen, 79%, of oxygen, 21%, and CO2. It's a very tiny amount in comparison, 0.04%, or if you prefer, today, about 420 parts per million. There's also water. Water is variable, it might be about 5%, but a maximum, but that depends on the conditions. It's very variable. If you go in a very cold place like the North Pole, it's almost zero. But anyway, so why? This you know, but it is rarely asked why. Why 79% of nitrogen? And we don't know exactly why, but the very fact that there is nitrogen in the atmosphere indicates that there are reasons for it to be there. And because if it were not continuously recreated by biological activity, this nitrogen would disappear in probably a few million years, transformed into nitrates, inorganic solid compounds. If they exist because some bacteria are able to fix it, to transform into compounds, which can be then used by the metabolism of the life forms of Earth. Even we need nitrogen in forms for our molecules, in form that can be metabolized. We cannot breathe nitrogen as it is. And that's part of how the system, the biosphere, is alive. It's a complex system. It's continuously cycling materials. If there is something, it means that there is a reason for it to be there. But it's even more important for oxygen. Oxygen, 21%. And you know that oxygen is a very reactive molecule. And it was an intuition by Jim Lovelock back in the 70s. He said, well, look, if there is oxygen in an atmosphere, any planet, then it means something creates this oxygen, because oxygen is so reactive that it will react with metals and other materials in the rocky crust and disappear quickly. Oxygen would very rapidly disappear from Earth if it were not continuously recreated by photosynthesis by plants. And we have also some idea why it is this value of 21%, because during the past, some 350 million years in the past, the age of big animals and big plants, animals like us, it never went much higher than this, a little higher sometimes, but not so much, and it is believed to be a limit generated by the tendency of biological materials to burn. They're mainly of carbon burns, you have wildfires, and if it were much more than this, the whole thing would burn, something that evidently we don't want. But the more oxygen there is, the more active metabolism can be of animals. I'll show you that in a moment. Then we have carbon dioxide, which is a tiny amount, yet it is all important. It is sufficient for a lot of reasons. And why this is the tiny amount? Some people say, oh, look, it is so little. What do you think? You can tell us that so many things, so many bad things like global warming, climate change, hurricanes, all the rest are happening just because 0.04%. And you would be tempted to tell them, okay, it's a tiny amount, but tiny amounts can do a lot. Try swallowing a cyanide pill and then you tell us how you feel. That's nasty. I will not say that to anyone for real, but anyway, even small amounts can have lots of back effects. And from this, I would like to tell you now what CO2 can do, and it can do a lot of things. Let me show you. Wonderful molecule. It's unbelievable how many things happen in the biosphere because of this molecule. First, properties radiative forcing. And as you know, because we've been discussing so much about global warming, how does it work? It works like this. The Earth is heated by the sun. Sunlight is in the visible part of the spectrum. So it goes through the atmosphere, is not absorbed, hits the ground, essentially. The ground re-emits this light in the form of infrared radiation. This molecule can absorb it in the form of vibrations. When it interacts with a photon, an infrared photon, it becomes vibrating and it absorbs it, and then it releases this by transferring this energy, this vibrational energy, to other molecules in the atmosphere, because the atmosphere is very dense. 0.04% of this molecule, it is a lot. It's sufficient to make sure that an infrared photon, indeed the right wavelength, does not travel more than maybe 20 centimeters in here, where I am now, in this atmosphere, in my room, and that's sufficient to block all the radiation that comes from the ground and to keep the surface of the Earth much warmer than it would be, and that's what we want. So why is it used to be 280 ppm during up to the start of the industrial age? Because before, during the Pleistocene, it was 180 ppm, and today it's 120 ppm. Earlier on, in very ancient ages, it could be millions and millions, hundreds of millions years ago it could have been 1000, 2000, it depends. It is an equilibrium, it's a homeostasis created by the Earth system, which compensates for other factors, mainly the fact that the solar radiation grows very slowly, increases over billions of years, and it is now somewhat higher, not so much, but a little higher than it was at the time of the dinosaurs, for instance. And so the system, among other things, not just this one, but among other things, tend to compensate for this higher energy that comes from the sun by reducing the amount of CO2, so reducing the greenhouse effect, or radiative forcing, which is a more correct way of saying it. And so that's why our ancestors, remote ancestors, at the beginning of the story of the Homo sapiens and our earlier ancestors, they were breathing about this value of CO2 during the Ice Age. They were born, we were born with this kind of CO2 concentration. Now we have this, and this is bound to have consequences, and we will see a little more about that. But this is relatively well known, and the point I wanted to make is not so much to repeat things which are known, but things which are not discussed so much, like the other effects that CO2 has on the biosphere. One other one is acidification. Because CO2 is not so reactive, as you say, but it reacts with water. It picks up a molecule of water and it becomes carbonic acid. Carbonic acid releases one or two hydrogen ions, creating a more acidic environment in water. Water means the oceans. And the acidification of the oceans is called sometimes global warming's ugly brother, because it is known, it exists, it's been known for 50 years. It is known that it does a lot of damage, like if you have a calcifying organism like a coral or a seashell, you don't want to have an acidic environment, because carbonates tend to dissolve into acids, and that's happening, but we don't know how bad it is, we don't know if there is a limit. Probably there is, but it has never been established, so, and it is discussed much less than global warming, because probably we are not marine creatures, we are not seashells, but it is important. And it also acidifies your blood, because your blood is mainly water. And so you have CO2 which goes inside your blood, it should, because you have to bring it out from your body. And there is a whole series of effects that this acidic environment causes your body to react to maintain a specific level of acidity. How does it do? For instance, by mobilizing calcium atoms from your bones, and all those series of consequences. It's a long story. Not necessarily good, but not discussed. Then 3, photosynthesis. And you know what it is, photosynthesis. It is how plants use CO2 through what we call oxidation, where they break down water molecule, create one hydrogen atoms, reacts with CO2, and you create sugars. It's the fundamental reaction which creates life in the atmosphere, because every single atom of carbon inside your body was once a carbon dioxide molecule, part of carbon dioxide molecule. Then it went through the photosynthesis, was transformed into sugar and other compounds. The plants were eaten by animals, and you ate the plants or the animals, and you became, your body was created by those molecules. And then when we die, these molecules, these atoms of carbon, are returned to the ground, reoxidized, retransformed into CO2, picked up again by the plants, and there it goes, as we said before. Everything which exists in the biosphere and the wider ecosphere exists because there is a cycle, otherwise it will not exist. So the photosynthesis has CO2 as a reactant, so you would think that more CO2 is better, which is probably true, and too little CO2 could be a problem, and that is also true. This is also another intuition by Jim Lovelock in the 1970s. He said, hey, look, people, if you keep, the sun keeps radiating more, and in order to compensate, the atmosphere reduces its concentration of CO2, then eventually you reach a point in which you don't have enough CO2 to keep the photosynthesis reaction going, and everything dies. Not good. And some Lovelock estimated that the limit was about 150 ppm. And I told you that during the Pleistocene, a few million years ago, we went close to that. We have seen that the destruction of the disappearance of the biosphere, maybe, but in reality the situation is much more complex than this, because it's not just one kind of photosynthesis. There are two kinds of photosynthesis. One is a traditional one used by trees, and the other is another kind which is specialized to operate at low CO2 concentrations, and that's typical of grass. That's the reason why Earth is going through a huge transformation, which is probably going to see trees disappear to be replaced by grasses, but over tens of billions of years. So it is a story. And then, after this intuition by Lovelock, now some people notice, well, but if just there can be too little CO2, maybe it is good if we have a little more. And so people started saying, oh, CO2 is a good thing because it is food for plants. And it is true that now if you cultivate vegetables, I don't know, tomatoes, in a greenhouse, and you put some extra CO2 in the greenhouse, you have a certain increase in the yield of your products. And since you get more tomatoes, so you can sell them, you make a little money, and then in this sense, CO2 is a little thing, but it's a good thing, but be careful. What you do is mainly to cultivate vegetables which contain more water, not more nutrition inside them. You only have obese vegetables, and this is a form of obesity. If you push your cultivation with CO2, you create obese plants. It's the same for humans. You would not say that the person who is obese, a little overweight, a little bit, you would not say he or she is better because he weighs more. But this is what people say about plants. They are better because they weigh more, but it's a long story. So it is not going up in the atmospheric concentration in the global system is surely having effects on it. An effect which is called global greening. Plants grow a little more, but it is not necessarily a good thing. And then anyway, if you go over certain limits, the data show that the effect is reversed. But again, a long story, and you have to be very careful here, because people try to trick you in telling you that it is a good thing. CO2 is a good thing. It makes plants grow faster. Maybe, but we are not plants. And there is a fourth area where CO2 is having a big effect, which is respiration. Respiration is we animals, humans, we respire, we breathe oxygen. And it is the reverse, as you know, it is a reverse reaction to photosynthesis. Plants create sugar from solar energy and create oxygen as a waste product. Respiration, it's the opposite. We burn organic substances, so sugars, proteins, fats, etc., using oxygen, and we use them to create energy, to create specific molecules, which are called ATP, adenosine triphosphate, which are the element, the crucial elements in your metabolic system. You create energy from what you eat and you oxidize what you eat, but the energy in the usable form is these molecules, ATP. There are so many trillions created every second or something like that, and your brain works because you can send ATP molecules in large amounts into it. Now, what is the effect of CO2? Well, CO2 for an animal is a waste product. The problem for animals like us is that we create oxygen inside your body, CO2 inside our bodies by the respiration process. We have specialized organelles inside cells which do exactly that, combine oxygen to CO2 to create ATP, and the CO2 must be disposed of, otherwise it would accumulate in your body and you die, and that of course you don't want. And so how is it done? It's a little miracle which is called blood circulation. If you are a bacterium or you are a single cell creature, you don't worry about circulating air and CO2 inside your body, because you're just so tiny that you're continuously in contact with the ordinary air. But if you are a metazoan, as we are, then you have this problem, and you solve it by this incredibly complicated and effective circulating system, which means that you have a liquid called blood, which transfers oxygen from your lungs, you breathe oxygen, transfers it into blood. Blood carries oxygen in your body, brings it to your mitochondria, and your mitochondria release CO2, and blood takes the CO2 and brings it out. It's easy to say, but complicated, very complicated to do. It is not so difficult to have blood to carry CO2, because CO2 is soluble into water, in a watery liquid. So CO2 mainly moves inside your body as dissolved inside the plasma of your blood. And now it takes some work there too. We have probably know that we have a specific enzyme which is there expressly to make the solubility of CO2 into blood faster. It's called carbonic anhydrase. It's very important in the human metabolism, but it's another story. Then the problem is, how do you do that with oxygen? Oxygen is not easily soluble in water, a little, but not so much. So how do you transport it inside your body? And you need a special molecule, which is called hemoglobin. Hemoglobin, more or less exactly, hemoglobin. It has a special group inside, which is called the heme, which can bind oxygen. And since hemoglobin is soluble in the blood, then you can carry it around. Carrying this is like a truck, hemoglobin is a truck, carries oxygen to where it is needed. But there is a big trick here, a trick for the truck. And you don't just need to carry this oxygen, you need to release it when it is needed. And now, how does the heme know when it is the moment to release the oxygen? And this is the miracle of circulation, that it is a catalyzed process. Catalyzed by what? By CO2. Again, the hemoglobin molecule has this characteristic. It has two configurations, and when it binds to CO2, it goes through what is called an allosteric transformation, which means that it changes its configuration, and it bumps the oxygen out. And it's really miraculous, because when your hemoglobin molecules get close to the mitochondria, they find a lot of CO2 and say, oh, well, it's moment to drop the CO2, and bang, it goes. And then they pick up a little CO2 also, but the main, just about 10% goes to the hemoglobin molecule. The rest is dissolved in the plasma. But this is crucial. If this system doesn't work, you don't breathe. You need to bring oxygen to the mitochondria and take away CO2. It's fundamental. If it doesn't work, you die. And what does it mean? It means that your capability of oxygenating your tissues depends not just on the concentration of oxygen in the atmosphere, but also in the concentration of CO2. It is known. There is your transport of oxygen. It's directly related to the concentration of CO2. More CO2, less oxygen, and the rest is true. So it is a fundamental point which has an effect on your body. And this is the big trick here, that CO2 can be poison because it affects the supply of oxygen to your body, your tissues. This is, then of course, what is the limit? You know that the poisoning effects are very related to the dose. What is the dose that will kill you? Now, let's see, it depends. There is no simple threshold here, but let's see what kind of concentrations are harmful and which kind are harmless. So we said that during the Pleistocene, we had about 180 ppm. During the Holocene, which is the current age, we had about 280 ppm. Now, the industrial age, we have some 420, which is what is measured in Hawaii, on top of a mountain, but in reality, in an ordinary environment, in a town like where I am now. I'm in Florence, in Italy. It is a town, and I can measure it. Out of the window here, if I go with a sensor, which I have, I can measure about, because in a city you have all sorts of industrial activities, engines, stoves, and that kind of things. And then we can say that indoor concentration should not be more than 1,000 ppm. It is generally said, but not so many people measure it, but inside your home you should have less than 1,000, and possibly considerably less than 1,000. And I would like to show you what we have now inside this room. And the sensor can tell us, and it takes one moment to stabilize the sensor, but as you can imagine, it will not be the same concentration that can be measured on top of the Mauna Loa in Hawaii, and we will have even more than outdoor concentration. Let's see what it measures. Still a few seconds to stabilize. There we go. 753 parts per million. It's still stabilizing a little, but it is in this range, 750 parts per million, which is more or less in the safe region. But note that nowhere, never our ancestors, my ancestors, your ancestors, they were born breathing these concentrations, not these concentrations. So we think it is safe because there are no evident changes in the human metabolic state at under 1,000 ppm. But let me tell you that there is at least one study that shows that already at 600 parts per million, there is a measurable slowdown of the mental capabilities of the people exposed to it. It is one measurement, take it with a lot of caution, but it's we don't know exactly, but it is already, after all, if plants are already affected with 420 parts per million, you see this effect of global greening. It is not far-fetched that we see the same effect, an effect for respiration for humans around 600 parts per million. In general, it is said that a safe limit is under 2000 ppm. You should not go over 2000. On that point, if you go over 2000, you start having symptoms. That things start happening. You have headaches, and you can measure metabolic properties of your body, like acidity, like blood pressure, like insulin movements and things that are effects. So you should do something at this point. It is reversible. You go back to low concentrations, but it is not good. And very often, indoor, in your houses, in your homes, in workplaces, schools, and theaters, and conference rooms, you go much higher than that, way higher. Easy to measure 5,000, 6,000. And if you wear a face mask, you go even higher. With a face mask, you in a closed room, you go easily over 10,000. And there is another thing, the workplace. Which is said to be workplace limits, means that you work on a shift of 4 hours, you should not go above 5,000 parts per million, which is a concentration which people who are, say, submariners, miners, astronauts experience this kind of concentration. Of course, they don't die, nothing horrible happens to them, but they undergo significant metabolic changes, which the body, the metabolic system, changes in order to compensate this kind of effects. It's a very interesting subject which has been studied, and of course, in some conditions, you have to survive in these conditions. And consider a surgeon wears a face mask all the time. It probably goes way higher than 5,000 parts per million, but he doesn't die, of course, or she doesn't die, but he doesn't have to solve differential equations while he's on the operation room. So it's a surgery. Doing surgery is you need to know what you're doing, but it's not the same thing as creating or solving a mathematical problem. And just to give you some idea what is the limit, okay, of course this is an extreme, but if you are in a sunken submarine, or you are a miner stuck inside a half-collapsed tunnel or whatever, then you die, unfortunately, because you reach this kind of concentrations. But be careful, because it's interesting that people say that if you're stuck in a sunken submarine, you die because of lack of oxygen. No, you don't die because of that. You die because you are poisoned by CO2. You are poisoned by CO2 because even with 5% of CO2, you still have a lot of oxygen in the atmosphere. It's 5% of all the components, which means the oxygen you lose only maybe 2% of oxygen. For some 21 you go to 19%, which you would think, well, why not 21, 19%? What is the big difference? And yet you die. Not because you don't have enough oxygen, but because you're poisoned by CO2, which is not so inert as people say. And this is, you see, these are things of which we know relatively little, but they are important because the metabolic effects of CO2 are something that our body has been adapted over our evolution, millions of years, and now we're changing this concentration to values which are growing, not only much higher than they were in the past, but they're growing. And the big question, which I would like to explore in the next part of this talk, is whether our brain, which evolved in these conditions, our brain can survive in these conditions. It is a very interesting question that we are going to explore in the next part of this talk. And thank you for your attention up to now. Let me tell you something more, just
for a little relax. Acceptable 2000 and the workplace, safe, acceptable, workplace, and these are all parts per billion. Okay, so let me show you my slides. We move a little bit to something as much as possible, a little more interesting if we can. Less gloomy, but I think you would be interested about that. Okay. See it. Where is it? Just 1 second. Okay, there we go. Sorry. So let me start with something a little different, and which is, however, related to this. This is the Dinosauroid. Maybe you pronounce it like that. And it is an idea by Dale Russell, an American paleontologist, whom I met, I remember, in the 1980s, and we found each other to be brothers. We had some genetic similarities because we are those kind of people who know that we were born dinosaurs. Like it's too much of a fascination for many of us. The dinosaurs are such a wonderful thing. But Dale Russell, he's not anymore with us, unfortunately. Dale Russell had one of these ideas that you ask you a question that nobody asks, and then you try to find an answer. And this question was, why didn't dinosaurs develop intelligent entities like humans? And it try to think how this dinosaur here that you see on the right, which is called sort of like a troodont, an animal late Cretaceous dinosaur, it could, according to some ideas that he had, develop into an intelligent creatures. It looks a little like a human beings. Why didn't it happen? And according to Russell, said it is because of the asteroid came down on these poor animals and destroyed them before they had the time to develop intelligence like we do. But I think it was a great idea, but not completely right, because dinosaurs had been around for 90 million years or more, and they had all the time needed to develop intelligence if they were in the conditions of doing that. Because you see, the human brain developed in a very short time in geological terms, not tens of millions of years, but at most a few million years. And the big growth of the human intelligence happened no more than 300,000 years ago. Started with we sapiens appeared about 200, 300,000 years ago. So it is a fast process. It was very fast because the conditions were right. When the condition arrives, right, evolution happens very fast. And question is why? What happened that created this? And it is also, this is an incredibly interesting story because we have recent data from this lady whose name is Susanna Herculano Husel, who spent her life boiling brains and counting the neurons in them. It's an interesting job, I am sure. And she discovered that human brains are really special because we have a special gene in our genetic setup, which can create some dense, tight packing of neurons that few other mammals and a few birds have this capability. And humans are really another kind, a different kind of creatures. We have very special brains in comparison to elephants, for instance. Elephants have big brains, but not so dense in terms of neuron density. We have big brains and very dense. And so that makes us intelligent, more or less so intelligent that we behave in very stupid ways, but that's another story. So the question is why? And the people have been thinking about that. So why did humans develop this highly packed, tightly packed brains? And people say to keep alive such a big brain, mine is not so big, I don't think so, you need a lot of oxygen. And so why do mammals of the Pleistocene had so much oxygen? Because really, if you go see the evolution of oxygen, you see that our time, you see it on the right side of this slide, which is very uncertain. Don't take it as anything more than approximating oxygen. We don't have very good proxies for oxygen, but we know that it has been more or less stable during the past 350 million years ago. And our times, Pleistocene, the Neogene, it was even a little lower than before. So you had oxygen, but not so much. The dinosaurs had oxygen, possibly more than us. So why didn't they develop big brains just like they develop big bodies? And I think there is a reason. And I present you this hypothesis of mine, and I'm presenting it to you. It's an idea of mine. Don't take it as established science. You may say it is something made by the rear end of a brontosaur, if you like, but I think it is possible that it is CO2, again we return, CO2, low concentration of CO2 that makes it possible for big brains to evolve, because I told you about the mechanism of a change of CO2 with oxygen in the body, and the less CO2 you have, the more oxygen you have. And my opinion, that makes it possible to have these big brains with the high metabolic requirement. If you take the oxygen to CO2 ratio, you see that there is a logic. It goes, we are now in a point in the long history of the Phanerozoic era, we are at a point when you had a maximum. Never had such a high ratio of oxygen to CO2, and never had intelligent creatures like humans. And this is an hypothesis. I leave it to you to think about that. The problem is that if you plot the most recent data, you see that by increasing the CO2 concentration in the atmosphere, we are going back. We're going back now to the mid Cenozoic, when humans did not exist. So the question is, can humans exist with a concentration of CO2 which is as high as it is now and growing? I leave the question to you and to judge. But one thing that we're noting is that there is such a thing as global dumping. People are getting stupider. That's, I think it's evident what's happening in the world, but it is not unthinkable that this effect of reduction of the average cognitive performance of human beings is due to this increase in CO2 concentration. So what's going to happen? Yeah, I'm optimistic. I'm optimistic. We have this data, recent data, about what's going to be the future. We humans are giving a big perturbation to the system, huge perturbation to the system. And but don't worry, it will disappear in a relatively short time, in a million years or so. The oxygen, the CO2 that human pumped into the atmosphere will be disappear, and then we have probably 500 million years of relatively high oxygen concentration and diminishing CO2 concentration, which means that we probably will return to the conditions of the Pleistocene with these huge steppes and big animals and hunters, and not human, because we will probably go extinct much before that, but that's a possibility. The Earth is not going to die because of the perturbation we are submitting it. We are imposing it to it, and so it is good. don't worry, whatever happens, it will happen because it has to happen. And I conclude here, and you see how wide this molecule, these 3 atoms, how wide consequence, how important it is for the ecosystem as it is now, as it was in the past, and as it will be in the future. And let me thank my sponsors, the goddess and Lord Ganesha. and thank you very much for your attention.
Thank you very much, Ugo. And I encourage people to put their questions and comments in the chat. And you did not mention your book career. And I think I shared with you, as a prerogative of the host, I get to ask the first question. So I'll just, I'm finding your book, Exterminations, very difficult to read. Yes, your latest book. And not because the language is bad, but because it's such a horrid story, quite frankly, of exterminations through history. And I'm actually interested in hearing, as an author, was this a particularly difficult book for you to write?
That's an interesting question. I think it was what you called sometimes a catharsis. You know what is a catharsis? Cleaning, because
Yeah.
I, just like you, I felt depressed, and because the situation, because how things are so horrible right now, and I writing then things down, I sort of removed it from inside and putting them outside, and we can discuss this with people. And I think we don't have to hide this thing. If you hide your problems, you make them worse. So they have to be made explicit, and this is what I did with this book. If you like to read it, I understand that it may be a little depressing, but not so much. Some people told me that they found it engrossing and interesting, because really it is not a pessimistic book. Unfortunately, we humans have this idea of killing each other. It happens all the time.
And then the first person in the chat that has come up with a question, Mr. Ranjbar, can you unmute and
Okay, let me see. Do I see this question? No, I don't see it.
no, it came to Art actually, and then Art sent it to me.
Okay,
there we go.
Please,
and
please.
So please feel free to ask your question, Mr. Ranjbar. We don't hear you, even though it doesn't appear, you don't appear to be muted.
Mr. Ranjbar, why don't you write your question so we can read it?
Actually, he has, and I through Art, I will go to it and let's see. Every day, a considerable number of people die and are buried under the ground. Is it a kind of carbon capture?
No, it is a part of the cycle. The biosphere continuously cycles through living creatures and then dead creatures. You have, when you die, you simply give back the CO2 you gain from the atmosphere through plants, and it is not in itself a kind of carbon capture.
And I will parenthetically add, because of the wonder of Google, that Mr. Ranjbar is a researcher publishing at ResearchGate from the University of Tehran, and he studies the desert ecology, if I can kind of generalize that way. So we're delighted to have your question.
A pleasure, Mr. Ranjbar. Which university are you in Tehran?
Shiraz.
Shiraz
And
University.
we still
Shiraz,
can't hear.
Shiraz.
Yeah,
No,
we
we cannot
can't hear
hear
you, Mr. Ranjbar. Sorry.
Okay, never mind. Thank you for the
But
question.
you're very welcome here. And let's see. we're kind of a dearth of questions. I see that Bill Reese was on the presentation. Maybe I'll just put him on the spot. Bill, would you want to ask a question? And I encourage everyone else, don't be shy. You usually aren't. Please put your questions and comments, although please try to keep your comments short and turn them into a question. Go ahead, Bill.
I'm an ecologist and former member of the Club of Rome as well. The Gaia hypothesis is such a brilliantly intuitive hypothesis and has been accepted by some of us with great enthusiasm, and yet is generally a lot of scientists are very reluctant to take it on. Why do you think that is? Why have we been so reluctant to accept the Gaia hypothesis, the fact that life can self-regulate the ecosphere to sustain itself?
I think it is because scientists usually that's too serious, you know, probably. I use the metaphor of Gaia in my blog. You can see it, and I find it a lot of fun. So maybe true, maybe an approximation, maybe also, but it's so interesting, so fascinating, so amusing that I keep using. And I think we scientists, we should be a little more light somewhere, to accept these kind of ideas for what they are. They are illustrations. They are not heavy science like the thermodynamics principle. But I think there's a lot to say in favor of Gaia, and the lady helps me in my presentations.
Thank you very much. Yes.
Thanks for your question.
Okay, Art, you're free to ask your question, and I think Dave Pollock is on deck, so you can show us your video. And please continue to put your questions in, or at least reference that you have a question into the chat.
Yes, Ugo, I have read some of your other material and have shared it with some of my colleagues at CACOR. And I do have this question with regards to our ability to reproduce, and sperm count is dropping. Is that related in some way to CO2 concentration?
This is a very good question, because it has not been said. In the literature, we don't have this statement. And it is an idea of mine that I can propose to you that maybe it is one of the causes, but I cannot prove it.
But then you do have evidence, I believe, that the reproduction ability is dropping in humans. Is this also happening in other species?
Yeah, that's in humans. It is very clear. We have evident data that we have a chemical effect, which may be just one of the effects, because correctly people say, well, don't forget the cultural and economic factors which make it cause humans not wanting to reproduce. So it is typical of complex systems. See, when you have like climate change, like climate system, you have several factors pushing the system in the same direction. Like in the case of the climate system, you have the radiative forcing of CO2. But there is a recent paper just this week on Science that says, look, people, we also see that albedo is decreasing. So you have these two effects which push the system to higher temperature together. And it is not easy to disentangle these two effects, because they all both go in the same direction. The same for reproduction. The birth rates are affected by cultural, economic, social, and chemical factors. Which one is the most important? I cannot say, nobody can say. Personally, as a chemist, I tend to see biochemical effects are more important, but there is a subtle and not so subtle point about this, because if it is a cultural problem, people decide not to reproduce, then it can be reasonably easily reversed. People say, there are no more children around, we have to do something and reproduce. But if it is chemical, then we have to clean up the mess that we created, and that's much more difficult and more expensive because things like CO2, heavy metals, aromatic compounds, and all this kind of stuff, the forever chemicals. You know, this is horrible name. The very concept that there are such things as forever chemicals. And we happily push them into the atmosphere, in the water, and in what we eat. It's unbelievable. That it is true. It's extremely difficult to get rid of them, and they will stay with us for millennia, probably even more. So you see, there is a difference in not in the cause, but in the solution, not in the problem, but in the solution. And I hope that it is more cultural than I think it is. But if it is biochemical, it's very difficult.
Okay, thank you.
Okay, David, you are up, and Phil, you are on deck.
Thank you. Ugo, had you been my chemistry teacher, I would have paid much closer attention and enjoyed it a lot more than when I was in school.
Thank you.
The question I have is, when you were talking about people's cognitive ability decreasing with the increase in CO2, have there been a lot of experiments validating that with a lot of peer-reviewed research? Is it a settled conclusion, or is it still in the area of a hypothesis? I wasn't quite sure from your presentation.
That's a very good point, David. I would love to have students like you, actually, as you said, because I would, from what I know, we are together with some co-workers, we are writing a paper on this subject. Let's say that it is more than a hypothesis, but less than a proven fact. We need to do much more work. I think there is largely enough in terms of the data available to know that there is a problem, but quantifying it is not so easy. And as we move, as usual, as we want to be sure that that the dam is bursting out, then by when we are sure that the dam has already burst out. So it's a usual problem.
I would think it would be fairly easy to get various greenhouses with researchers in them and pump different quantities of CO2 into.
It has been done. It has been done. Studies of people at different statistical studies of people exposed at different concentration of CO2 a lot. A lot of these studies have been spurred by the use of face masks. Face masks cause you an increase in the concentration of CO2 that you breathe. And a lot of studies have been done in that, and the effect is there. Not you don't go dumb. Okay, if you are a surgeon, you wear a mask all the time and you keep doing your job, so it is okay. But you don't do it 24 hours a day. So it's a ongoing story that we are learning.
Thank you very much. Good.
Okay, Richard Vanderjagt, you're on deck, and Phil Riley, what is your question?
Yeah, thank you very much for your presentation, Ugo. Just as a brief introduction before I ask it, my training has been as an ecologist, and my practical life has been running a plant nursery with a focus on ecological diversity and the production of food. So with the idea of production of food, I've noticed in the literature within the last few days that there is a huge presentation by industry to adopt precision fermentation as a food source rather than growing food naturally on ecological grounds that also support us. Food is just one of the very few things that we need to exist. Your comments, please.
Thank you, Phil. I think as an ecologist, you probably know more than me on this subject. What I can say is I can cite the story of the guy who jumped naked into a thorn bush and then when they took him out, they say all bloody and say, why did you do that? And he said, because it seemed to be a good idea that this precision fermentation seems to be a good idea. It actually seems to be an excellent idea. But we have to see, of course, whether it works as it is promised.
You know, the difficulty is that with it, you ignore the natural environment and you install huge industrial plants to marry carbon dioxide, oxygen, and nutrients to produce. And I don't know what it is they're going to produce. I think it's all going to be liquidy types of stuff, maybe as solid as cheese, but nowhere near that of meat.
Yeah, it could be. We don't know. It's anyway. It is a very interesting situation because people have been worried so far from the time of Thomas Malthus. They've been worried. We have lots of people and not enough land for agriculture. If by any chance this thing works, then we will not need so much land because with a much smaller footprint we can produce a lot of food. But because of chemical pollution, we won't have so many people needing all that food. So it's you see how things change so fast. It's unbelievable. But we live
But the
in changing.
the implications of this technology is that we don't need to limit population.
That's right. But you see the point. I don't know if you had a moment to read the post that I wrote this Monday. I said there are two things of population collapse. The one is Malthusian. Don't have enough food. Population. It's everybody wants to reproduce, but they don't have food, so they die. This is Malthus, and it's true. It happened many times in history. Then I proposed a different kind of population decline, which I called Carsonian. You know Raquel Carson, as an ecologist, you know her, and she was the first who proposed there was a huge problem of chemical pollution on the planet, and then in that case you have food but your metabolic system is poisoned by the pollution you create by your industrial system, so the population collapses, but not because of food. Maybe that's the future.
Thank you very much.
Okay, Ted Manning, you're on deck, and Richard,
Thank
you have the floor for your
you.
two questions. You have a question and a comment. Go ahead. We have lots of time.
Well, further to a couple of things you said. One is the declining sperm count for sure has been related directly to environmental toxins, and I think that has to be taken into account when doing these calculations. But the bigger thing is the bigger problem as I see it. CO2, once it's produced, it's in the atmosphere for many decades. And regardless of what we see as a solution, the solution that we invent today, carbon capture, we know doesn't work. So it's going to take many decades to have an effect. So that means there has to be a joint collaborative effort against the climbing CO2 levels that we all know is toxic to us all. Would you agree?
Yeah, of course. But you see, the political situation is what it is, and right now we are in the worst moment to propose a joint global effort to capture or to at least reduce the emissions of CO2. And so I know it is dismaying. I don't know what to say.
Yeah, we wrote an article on that just recently on the wall that you have to cross to get across to politicians on why we can't get through to politicians to do something to decrease the
and you probably know
CO2
the failure, Richard. Last week we had the failure of the United Nations conference on a treaty on plastics, on reducing plastic production, and then nobody wanted it. The politicians, the lobbyists, the fossil fuel industry. The pollution from plastics is also CO2, because when you produce plastic, you also produce CO2, but also all kinds of nasty chemicals like phthalates and fluorinated compounds, all sorts of stuff. They're not good, even if you are a lobbyist for the fossil fuel industry. I mean, you breathe this kind of stuff yourself, and then nevertheless they go there they were in Busan in Korea, and they say, no, we don't want it because we make money on plastic, so we don't care about our own health and the health of our children. If you think about that, it is unbelievable, but it happens.
I agree.
Okay, John Legg, you are on deck, and Ted Manning, you have the floor.
Ugo, thank you very much. I very much what you also did in Brussels and got everybody excited too. I'm going to take a tangent off of this one. I won't get specific. I want to ask more. How big is the issue that nobody believes scientists anymore? That we can do wonderful stuff and suddenly it doesn't matter because nobody is listening to anyone who has not just science, any expertise. Have you any thoughts on how Club of Rome or any of us could actually try and address that one?
I don't know. TED is a disaster. I don't know. I am surprised, just as everybody else, the sudden collapse of science. It's unbelievable, and nevertheless, it has happened. So it means that we did something wrong because we are the scientists, by all means, and we did it wrong too. We did many things wrong actually, and self-reference and corruption and plain ignorance. Many people are so specialized that they are completely dumb. They don't know anything except their specific field. And I don't know what's going to happen. There may be a reversal.
I can remember a time when the odd politician would actually go and have a beer with a scientist, and that appears to have changed.
Absolutely. I have the same impression. There was a time when politicians, before taking a decision, they would ask scientists, what do you think? Not anymore. That has disappeared. And this is a tragedy. But as I said, there is no problem we are creating now that will not disappear in about 1 million years.
So can we make people do anything about carbon dioxide?
Sorry?
Can we actually convince anyone to do anything about carbon dioxide?
A few people are convinced. I think there are still opportunities to think of something intelligent if we have some hopes.
Well, thank you very much, Ugo. Always nice to hear you.
Yeah, same to you, Ted. It's a pleasure to see you every once in a while.
Okay, before John takes the floor, looks like Bill Reese has one more comment. I'm going to take that as an opportunity to bring you back, Bill, to dialogue. So go ahead, John, you have the floor.
Yeah, well, my comment was quite simple. You meant, oh, sorry.
Well, that's all right. That's our confusion. We try to make sure that someone is ready to go the next time. So being on deck means that you come after John.
Yeah,
it's okay. So go ahead, John. John Legg, we can't hear you. Yeah, microphone.
You're muted, John.
How about that?
There we go. We hear you.
Okay. Ugo, it was fascinating to review the processes that CO2 undergoes, and I think I understand the main hypothesis, that is your hypothesis that the brain's capacity to reason decreases as the level of CO2 increases. So the natural question, it seems to me, is to ask you to please speculate on the results of this process. And to put my question more bluntly, because Homo sapiens is not doing well with the present situation, please speculate on what Homo stupidus will do.
It's a very good question. It's a very interesting question. I've been speculating a lot. And my idea is this: the ecosystem, whole ecosystem is evolving. And it's, again, an idea that goes back to Jim Lovelock, who was the first to speculate on these things. So we're going in a future in which we will have less CO2, less and less and less CO2. Because the system is evolving, it's becoming a little bit a little tired from the viewpoint of geothermic, geological forces, so it emits less CO2, and also because the sunlight, the irradiation intensities is going up, so there is a a window of opportunity during the next 500 million years, in which CO2 will go down and oxygen will stay constant, more or less. And this will be an age in which the whole ecosystem will change shape. Trees are going to go extinct because they cannot live with so little CO2. And the world will be all a large steppe grass all over, because the grass is better adapted to low CO2, and grass can support large animals, like it happened at the end of the Pleistocene with mammoths. The mammoths will return, or something that will look like mammoths. And there will be space for creatures much more intelligent than us, because they will live in an atmosphere with even less CO2 than we had when Homo sapiens evolved. And they will be much smarter. Question is, will they be wiser? This I cannot say. But if you wanted speculations, you had it.
Well, I think you put your finger on it. Intelligence is one thing, but wisdom is another.
Yes.
And I will resist giving my own views of particular individuals in the upcoming few months and years. So thank you for that speculation. But I guess a summary of that is that because you're talking about quite a few years ahead, we should not hold our breath.
That's right. For holding your breath for 500 million years would be a little long.
Thank you.
Okay, Bill Reese is up. There's no one on deck, but we can improvise. And I have a comment. Maybe I'll shake things up. Go ahead, Bill.
Okay, thank you very much, Claude. I just want to sort of carry on from the last discussion. Again, as an evolutionary ecologist, I would speculate that the human brain, as complex as it is, evolved in very simple times. And as a result, humans tend to think simplistically. We tend to think of singular cause-effect relationships. We do not connect the dots. We're not really capable of coping with very large systems complexes. At least most people are not. And yet we've created a world of mind-boggling complexity. So I've written a paper recently arguing that we have made ourselves cognitively obsolete, that the cultural environment, our technological environment, has evolved much more quickly than our biological capacities to deal with it. So we're simply out of league, out of touch with the reality within which we have imposed ourselves. And the best example came up in an earlier part of this discussion. If you think of the current reluctance of politicians to act on any of this, it's because they have fixated on a singular thing, and that is the economy. Any activity that is likely to interfere with economic growth or population growth will be disregarded. It's simply antithetical to the current global paradigm of growth-based economic reality. And of course, now most countries are trying very desperately to implement pro-natalist policies to maintain population growth. So again, this is a singular fixation on a single issue, the economy, which completely ignores the biophysical realities within which the economy is embedded. So everything will go wrong, which I really take to be the gist of Ugo's presentation, that when you mess with a very complex system, when you have very limited knowledge, everything is likely to go wrong. Any comment, Ugo?
I totally agree, Bill. You said it very, very nicely and very well. As an evolutionary biologist, you know these things better than me, of course. So you stated the question very, very clearly. So we are going to clash against our limits. We are so smart, but not wise. And let's hope for the best.
Listen, I've really appreciated your presentation, and nice to meet you again.
Thank you.
And I have to leave now. I'm sorry. Right. Bye-bye now.
Okay, it was a pleasure.
Thank you, Bill. I resisted the temptation. I have a couple papers by Bill Rees that but I don't think it's the one that he was referring to, so I won't put it in the chat. So again, I'm going to take the prerogative of the host and suggest something that came out of the earlier conversation with other people, is that we have to get the politicians and the people in power to pay attention. And Ugo, I actually think that that they know everything that we know. Maybe not, they don't pay as much attention to the details.
Do they? I'm not sure.
I think they know, and the big fear is that we bring about a collapse sooner than it's time. So the panic becomes the enemy, not, because if it is too late, it's too late. And
it could be. I have a comment on this that I was reading. I was listening to a talk given by an ecologist at the Busan conference, whose name is Jane. Just one second, because I don't find the complete name anymore. But Jane Munker, she was at the conference on plastics in Busan in Korea, and she said that Nate Hagens, who was interviewing her, he was asking her, but how is that people, the negotiators, don't understand these points, which for us are so simple? I mean, you have plastic pollution, you can measure it, you can see the effects on the bodies of animals and humans and everybody. And they said, Nate, I think they really didn't get it. They couldn't grasp it. They were not stupid, but confused. And said that this is not a question of data. She's a very smart lady, this Jane Monk. She's not. It is a question of perception. And she said an incredibly interesting sentence: "You cannot buy the data, but you can buy the perception." And that's, I think, is a fundamental point, that these people who were negotiating against themselves, because that's what we're doing, were bought by money. The big problem is that your perception can be bought by money. And this is unbelievable, that you are going to pay, you get paid to commit suicide. Would you do it? I don't know whether the test has ever been done, but what happened in Busan, I think, is close to this kind of a situation.
thank you so much. Art has another question. So Art, if you could there you go. Turn on your.
Yeah, I just want to go back to the theme of your presentation in terms of saying that CO2 concentration increases, we lose our cognitive ability. But of course, these things, are gradual. I don't believe it's an overnight thing. And I'm thinking back to the complexity of the number of things which we make. You just think of an automobile. How many skill sets are necessary to be brought together to build that, or the electrical grid? How many skill sets are there in the world's largest and most complex and expensive system? Now, as or at least the way I look at it, this is in fact, at a peak right now, and whether it's going to continue to climb or it's going to start to decline in terms of the complexity of things that humans are building. Can you see a time when, in fact, we're going to lose these skill sets, or they become so eroded that we can no longer repair? We can't repair the dam that's generating electricity, that we can't grow the food because we're losing agricultural capacity. And You know, I'm just looking more at the transition period. How does that really manifest itself?
It's an interesting question. Again, you see, I've been using models for a long time by now. Models can tell you a lot of what may happen in the future, but they are rarely quantitative. So your question is correct. You say, when is it going to start, this collapse? The model can tell you that the collapse, if it starts, it will be abrupt. It will be a very sharp decline. It is what I call the Seneca effect. You may have heard of it. But it cannot tell you when, because that's very difficult. These things are phenomena which grow out of positive feedbacks, which accumulate, and then at some point something starts, some movement starts. They are akin, kind like landslides or earthquakes. And there is a moment, you know, that there is a hill which may go. Do you have a landslide in landslide in the making, but it's extremely difficult to say exactly when it will start. So that's the situation in which we are. The situation continuously evolves. And what changes is technology. If things stay as they are now, clearly we are going to go to a very sharp decline, a cliff. But things may change. We may develop new technologies like we were discussing, precision fermentation. Precision fermentation can help us avoid the agricultural cliff, the famines, and that could be a good thing if it works. And so we have to be flexible and hope for the best.
And just a related question is, how do you view this growing interest in AI, in artificial intelligence?
Well, that's another point that we are all surprised by this rapid development. Right now, these things are not so intelligent, as you will have noted yourself. They claim intelligence, but poor things, they're not very smart. But that's one more of those things that then they go up, and you lose track of what's going on. It can be very good or very bad. And I don't think any one of us, not even Elon Musk, can say what's going to happen.
Okay, thanks for your answer. Back to you, Claude.
There seems to be a silence here, so perhaps we have run the course of these conversations without getting too far astray from the theme.
Yeah, a little bit, yes.
Don't you have
Ugo,
Rick
what's your next
Carpenter up?
project? Can I ask on camera, since we have a little extra time, what is your next project?
My project, I'm working at a paper on this subject. I'm working at publishing it, which seems to be very difficult because this publishing system has become so tightly controlled, is so hostile to innovation, that even publishing a paper which says things which are basically known, and it is becoming very difficult. But we are trying to do this and see if we can move a little bit the consciousness around on this problem, the problem of CO2 as a pollution agent. And it is essential that our idea is to counter the public relation campaign that you have seen around, which aims at casting CO2 as a good thing. Food for plant, more food. It's nice to be a little warmer. And you see, it works. A lot of people are believing in this. So we're trying in our minor capabilities to provide data to contrast this interpretation, which is another one of those suicidal efforts that humankind is making.
So Bill Reese might be a good resource for you, as he publishes his papers in various places.
Yeah, that could be. We could ask him to give us a hand.
The Swiss-based MDPI has a climate journal. They have many journals, and he
Yeah, I know
chose.
MDPI, yes.
Okay, yeah.
Bill Rees. I will contact him. Yes,
Okay.
he's a very smart guy. Everybody in CACOR, in Canadian club, very smart, of course.
And like you, he doesn't give up.
Oh, that's good.
Because if you go back and, his warnings have been very dire, and he's very consistent in, the science behind his conclusions. And I was going to save this for the unrecorded, but since we have a couple minutes here, he was interviewed by Nate Hagens. And very shortly after that, Nate Hagens started working for Resilience, which is a creature of the Post-Carbon Institute, where Bill Rees is an advisor among many other people who are advisors. So there's a community there, and I think the networking is really what will help you get published, what will help you get noticed. And I wish you Godspeed in your efforts. So,
Okay.
Ted, you were briefly on the screen there. I think it is time for our official thanks.
I can't get on the screen until somebody allows me to. It says the host has blocked me.
That would be Art.
Now I can start my video, I think. Hello. That's okay. I didn't need to see me anyway. But as always, it's wonderful having Ugo to talk to us. Definitely can be depended on to bring new aspects into a conversation and to get people to think. And that is definitely what we hope to be able to do through CACOR and through the other elements of the Club of Rome, to get people to talk to each other. And admittedly, we are a little bit saddened by the state of reception of good ideas and good thought. And that remains a major challenge for us. And again, back to our own people, that it remains a continuing challenge to try and more effectively get information in front of people. And we have certain members who've been, even like you, writing books for the public, as well as writing academic papers and so on. The notion being, we are now just to recognize some things that some of our members have done very recently, putting videos out, short videos aimed at the public to try and attract their attention so that they can then look beyond whatever they were told last. So thank you again for talking to us. It has been wonderful again. And I'll just, again, thank you on behalf of our organization. And we must keep doing this as we keep going, mobilizing everyone we can. I would ask everyone, please, to have a look at the letter that we have sent you recently regarding the ability to pay your dues this year. We do base our ability to put this out to the public, to put out publications, to put out videos, and all of the above. So we would ask you again to please give us some money this year so we can keep doing it. And on that basis, we're able to get a lot of really good people to come and talk to us. We get to ask them embarrassing questions, and we get to do what we need to do to get people to really clarify what they mean and what they think everyone should do. So thank you again. And we'll simply say, if anyone misses this, it is available on the YouTube within a day or two. And we would ask you again to subscribe to our YouTube site when you watch it, because that gives us a little more reach when we do that. So thank you again, Ugo, and thank you for visiting us. Please come and see us for real at some point.
Yeah, it would be a pleasure, really. And thank you very much for this opportunity. This is a new thing for me, and I'm pleased to be able to present it to a public who can understand it. Not everybody can understand.
Well, we claim to.
We are pleased to be.
Right.
Hello, my name is Claude Buettner, and I have the honor